Walker L. Cisler Lecture Series was established at Lawrence Technological University in 1995 with a generous gift from the Holly Foundation in honor of Walker L. Cisler, who served as a member of his board for many years. Well known for his leadership of the Detroit Edison Company from 1954 to 1971, Walker L. Cisler enjoyed a career that spanned a lifetime of personal, professional, and civic accomplishments. As an international ambassador for the American electric utility industry, he worked closely with heads of state both here and abroad. As a tireless, dedicated humanitarian, he strived to improve the quality of life for people everywhere. Mr. Cisler was also director of the Thomas Alva Edison Foundation, an organization dedicated to inspiring and rewarding an interest in science among young people. Mr. Cisler is quoted as saying, "Science, engineering, technology, and, accordingly, the country cannot prosper until we once again produce a truly scientifically literate populace." The College of Arts and Science is pleased to welcome you to the 2019 Walker L. Cisler Memorial Lecture. And at this time, I'd like to invite our president, Dr. Verinder Maudgil, to say a few words of welcome. Thank you.
Thank you, Mr. Dean. Good evening. This is after dinner lecture. Good evening. Now you're there. Thank you. Well, this is an exciting evening or night at Lawrence Tech. I have attended many lectures. They are very preeminent lectures. The selection of lecturers for this evening has been the top grade ever possible. We had Nobel Prize winners, creators, innovators, entrepreneurs, academics, philosophers, and tonight is no exception. We have with us a person of eminence who is not only a contributor to welfare of this country, but he's been invited to over 50 countries. You will have a more extensive introduction for her from our provost later. But I wanted to emphasize how important this series is, Cisler Lecture. It's almost a signal lecture series of Lawrence Tech, where the very important we can find or quote will be the speakers here. Today's or tonight's speaker has a special reference and value and interest. The world is at the brink of instability. This lecture could not be timed better, where you have president of the world's greatest power coming back empty-handed from Hanoi of the nuclear agreement, and nuclear power in North Korea, who denied that because they won't let their nuclear power go away. At the same time, the neighborhood where I grew up, India and Pakistan, are almost at war. Both are nuclear powers. In 1965, last time they had an extended war that lasted more than a month. I was 80 miles south of the border of Pakistan. I grew up in India. Every night there was a blackout, curfew order, universities, education, everything was closed. You were not seen outside your house in the night. Even if you have a matchstick burning, a reconnaissance plane will shoot you out, and the whole neighborhood will be gone. So there were blackouts. I've gone through that. Those days, neither Pakistan nor India had any nuclear power. Today, they both have it. So you know the time we are living in. So because of that, I think on its own, it's very important academically and otherwise. But given the time we are living in, I think leadership of this country and those of Western nations has to make sure that this beautiful planet is not destroyed by people who are not controllable or are not responsible for other part of the world or their own people. That's why I welcome you to this great lecture tonight. You have a treat waiting for you. And I thank you for coming this evening and being with us to hear what is going to be an outstanding, memorable lecture. Dr. Woz will lead the introduction. Dr. Sara Pozzi is our speaker, and you will hear more about from Dr. Woz. Thank you.
Thank you very much, Dr. Margell. So I have the pleasure of introducing Dr. Sara Pozzi. Dr. Sara Pozzi earned her Master's of Science and PhD in Nuclear Engineering at the Polytechnic of Milan, Italy, in 1997 and 2001. She is a professor of nuclear engineering and radiological sciences and a professor of physics at the University of Michigan. Her research interests include the development of new methods for nuclear materials detection, identification and characterization of nuclear non-proliferation, safeguards, and national security programs. Dr. Pozzi is the founding director of the Consortium for Verification Technology, CVT for short, a large consortium of 12 universities and 9 national laboratories working together to develop new technologies needed for nuclear treaty verification. In this capacity, she directs the work of 25 faculty members and over 250 students engaged in research projects within the consortium. Dr. Pozzi is the co-author of the Monte Carlo Code MCNPX PolyMe, which is used at over 50 institutions worldwide. She has published more than 400 papers in journals and international conference proceedings. She has been invited to present over 80 seminars, both nationally and internationally. A gifted instructor, her students have gone on to develop successful careers in national laboratories, academia, and industry. She is the recipient of many awards for her important work, including the 2006 Oak Ridge National Laboratory Early Career Award, the 2006 U.S. Department of Energy Office of Science Outstanding Mentor Award, the 2012 INMM Edway R. Johnson Meritorious Service Award, the 2012 University of Michigan Nuclear Engineering and Radiological Sciences Department Outstanding Achievement Award, the 2007 IEEE Distinguished Lecturer Award, and the 2018 Rackham Distinguished Graduate Mentoring Award. She is an American Nuclear Society Fellow and an Institute of Nuclear Materials Management Fellow. Please help me in welcoming Dr. Pozzi to the podium. Yes, she's coming.
Well, thank you so much for that kind introduction. It's a privilege to be here tonight. I am very excited to be here and to speak to you about the physics of nuclear nonproliferation. As was mentioned in the introduction, this is a very timely topic. So I'll take you from the discovery of nuclear fission all the way to today's events in North Korea. So I'll tell you that story tonight. So what you see here on the screen is the periodic table of the isotopes. It describes the world around us. And these isotopes are ordered from lightest all the way to the heaviest. So for example, we have hydrogen, helium, lithium, beryllium, and all the way through the metals and the actinides down here. So we'll be talking about some of these isotopes. But I promise in the lecture there are no equations. Now somebody's disappointed. So let's talk about the origins of nuclear physics. It was discovered initially that the atom is made up of a much heavier center, which is the nucleus, that contains protons and neutrons. And after that, initial nuclear reactions were discovered. In these reactions, the transmutation of nuclei from one to the neighbor was discovered. However, it took a long time before we understood that larger nuclei such as, for example, uranium, could split into two parts, and by doing that, release a lot of energy. So what you see here is a nucleus of uranium, and what you see here is a schematic of the fission of uranium, whereby when this large nucleus breaks into two, it creates two fission products. These products are about half the size of the initial nucleus. And so we go from a nucleus that's down here, very heavy nucleus, back into this region here of the periodic table. And that's revolutionary, right? And it took a while to understand that. When a nucleus of uranium fissions, it releases 200 million electron volts of energy. And that's a lot of energy. It also releases these blue dots, which are neutrons that fly off of the fragments. And that happens because the fission fragments are neutron-rich. And they're very excited. And so they have to de-excite by emitting radiation. So these fragments are also very radioactive. So let me tell you a little bit about some of the key players in the discovery of fission. There is Rutherford, who is widely renowned as the father of nuclear physics. And he discovered that the nucleus contains most of the mass in an atom. It's concentrated in a really small nucleus. However, he did not believe in the large-scale production of energy by nuclear reactions. Indeed, he called this idea a moonshine. And we know today that, of course, we can harness a lot of energy from nuclear reactions. Enrico Fermi was an Italian, and he worked in Rome in the 30s. And he was doing a lot of experiments using uranium and exposing uranium to neutrons and then looking at the products. He initially induced fission. He was one of the first ones to do that, but he didn't understand that he had induced fission. He thought the fission of uranium was impossible. And the reason he thought that is that in the literature, the mass values were not correct. And so his calculations didn't quite work out. It was Ida Noddack who was the first person to say that perhaps those fission products that were being observed in these experiments came about because of the breakup of the uranium nucleus. And she has a paper, you can look it up. It was published in 1934, where she talks about this fact. At the time, she was way beyond her time, and nobody believed her when she said that in that paper. It took a few more years before other physicists got to that point. Hahn and Strassmann were working in Berlin, and in 1938, they also found fission products, but didn't quite understand what was going on. So the explanation of the fission of uranium was given by Lisa Meitner. She was a refugee, and she was in Sweden. And on Christmas Eve in 1938, she was with her nephew, Otto Frisch, also a physicist. And she was skiing, and it came to her the explanation of the fission process. So here's a neutron hitting this uranium nucleus, forming a compound nucleus that then becomes very excited and unstable and pulls apart into two fragments and then splits. This is a very energetic reaction. It also releases several neutrons. So this was the beginning of the Manhattan Project, where this reaction was used to generate the first nuclear weapon. And after the war was over, Otto Hahn received the Nobel Prize for his discovery, and Lisa Meitner never got true recognition for her contribution. This fact is still discussed quite a bit today. And this shows the house where she was living, and there's a plaque there that reminds us of her contributions. So what happens in fission? The nucleus splits, these fragments de-excite, they emit these fast neutrons, and if there are other nuclei in the vicinity, those neutrons can go on to induce further fissions. This is what we call a nuclear chain reaction. So if we have enough of this material, we can self-sustain this reaction. So what do we mean here by special nuclear material? It's uranium and plutonium. These are the isotopes that can be used to sustain a nuclear chain reaction. These are also the main explosive devices in a nuclear device. So we call them special because we want to make sure that we safeguard these materials carefully. They're very special. And you don't need that much to generate a weapon, right? So for example, for uranium, we talk about needing about 20 kilograms. And for plutonium, the number is even smaller, about 8 kilograms. So what do we mean here by critical mass? Well, that's the mass of uranium or plutonium that can sustain a nuclear chain reaction. So there are enough neutrons generated in that mass that it can be self-sustaining. So there's a critical mass. There's also a subcritical mass. So that's a mass that's under that critical mass. My student here, Jennifer, is holding a subcritical mass of plutonium. Okay, and it's quite safe to hold in your hands. You can feel a little bit of heat from the decay of that plutonium when you hold that in your hands. But this is a subcritical mass. How do we get a critical mass? Well, we could have multiple subcritical masses and slam them together, and that way we can generate a critical mass. Or we could have one subcritical mass, and then by using what's called implosion, we increase the density of that mass until the mass goes critical. So those are two ways in which you can make a nuclear explosion. And those have been used for uranium and for plutonium. This picture here shows a plutonium reflected by an outside reflector. And what we use that for is to reflect back the neutrons and therefore make this go critical. So that's another way to make criticality based off of a mass of special nuclear material. So in the late 1930s, this phenomenon was understood, and it became clear pretty quickly that the energy released in these fission reactions could be used for two types of purposes. We could use that energy to generate electricity in a nuclear reactor. And here you can see the Fermi plant here in Michigan. But you could use that same reaction to build weapons. Okay, so clearly there's a tension between the pursuit of nuclear energy for peaceful purposes and the pursuit of nuclear weapons. This became clear pretty quickly after nuclear fission was discovered. So here, this is an interesting phenomenon that not many people are aware of. So we think about reactors as a man-made thing, right? But actually, uranium is found in nature. You mine it in the ground. It's found in caves, different countries around the world. And so there's a phenomenon that was discovered where there was a completely natural nuclear reactor in a cave in what is now Africa. So in this cave, the composition of the uranium was such that a self-sustaining chain reaction could happen when water entered this cave. So we had the right composition of uranium-235 and uranium-238. So I'll be talking more about those two. Those are two isotopes of uranium. And the 235 is the one that is really good at self-sustaining the chain reaction. The 238 is not so good. But the 235, you don't find it in nature as much. So when you look at something like this, you mine the uranium, and today the percent of 235 is less than 1%. But many, many years ago, approximately 2 billion years ago, that percent was about 3%. And that's enough to sustain a chain reaction. And so this natural reactor operated for lots of years as water made it into this cave and helped sustain the reaction. So how do we make a weapon? So I told you it's uranium and plutonium. And these are the two pathways. And uranium, we mine it from the ground and from caves. But what we mine is not the right uranium for the weapon. We need to enrich it. It's a phenomenon called enrichment. So how many of you have heard about this phenomenon? About half the room. So what do we mean by enrichment? We mean simply enriching or increasing the amount of uranium-235 in the uranium, which is the isotope that we want for the fission chain to happen. And one way to do that is to use centrifuges. So how do we do that? We mine the uranium, we convert that into a gas, a uranium hexafluoride, and then that gas we pass through these centrifuges. And these work by spinning, similar to a salad spinner, if you've ever used that, where you have wet leaves of salad, and you spin it, and the water gets thrown towards the side of the spinner because the water is heavier than the salad. This is just the same. So basically what you do is you have uranium-238 and 235 in that gas. So there's a little bit of difference, a small difference in the mass of those two. And the heavier, the 238, goes towards the edges of the spinning centrifuge, and the 235 stays in the center. And so you pull out this enriched 235 from the center. Because the mass difference is really small, we have to do that in stages. So we have to take many, many of these centrifuges and spin them, and it takes a lot of energy to do that, a lot of electricity, to do this enrichment process. But that's one way to enrich uranium until it becomes weapons grade. Now, the other pathway is plutonium. And plutonium is not an element that we find in nature. So we have to make it. And the way we make it in nuclear reactors. So we take reactor fuel that contains uranium, we put it in a reactor, we irradiate it for a while, and we take it out, and we have to separate out the plutonium from that was made by nuclear reactions inside a reactor. So both of these are difficult processes, right? Fortunately, these are both complicated technological processes. So it's not easy to come up with the special nuclear material that we need for a weapon. Okay, so let's talk a bit more about enrichment. So uranium enrichment, in this graph you see the percent of uranium-235 in the material. So this is where you start off, less than 1% from the stuff that you mine, and then you want to enrich it up to upwards of 90% to be used in a weapon. And this is the amount of work that it takes. So when you start off, it takes a lot of work to enrich, and you enrich it to about 4 to 5% for a power reactor. So that's nuclear fuel that we use in the reactors. And if you continue the enrichment, you go up You go up all the way to weapons grade. It's what we call weapons grade uranium. Okay, so when we talk about safeguarding the material, we want to be able to say, okay, is this fuel that we see here, is it reactor grade or is it weapons grade? Because our response will be very different if what we see is a weapons grade versus reactor grade uranium. Okay, so let's take a look at some of the key historical turning points that happened after the discovery of fission. So I told you fission was discovered in 1939. Then we had a world war that was ended by the United States dropping 2 nuclear weapons on Japan. And those weapons killed about 200,000 people. So after that, everybody pretty much agreed that this was horrible and we should do something about it. At the same time, the US became the superpower, right? They were the first to build this incredibly devastating technology. But then other countries started to develop that capability. And so we have the Soviet Union, weapons test, the Great Britain's weapons test, and so on. In 1954, President Eisenhower launched a program called Atoms for Peace, where the idea was, well, we'd like countries to have access to nuclear energy, but we don't want more countries to go into the weapons path. And so that was the first time that the peaceful use of nuclear energy was encouraged. In 1957 was the formation of the International Atomic Energy Agency that's based in Vienna. And that agency was formed to promote research and development for peaceful uses of nuclear energy and to apply safeguards. And this body is very important because it's an international body that is used then for the Non-Proliferation Treaty, which was the first major treaty to stop the further spread of nuclear weapons. Okay, so these are recently declassified videos that you can Google. And you can see, how terrible these explosions are. These were US tests done at the Nevada test site. And basically, this is a 15 kiloton equivalent weapon, 1951, a 14 kiloton, 1952. So these are about the size of the bombs that were dropped on Japan. So that gives you an idea. And these were the initial bombs that were developed, and these are fission bombs. But over time, the technology improved, and you can see the size of these things becoming larger and larger and completely out of control, right? So we're going from 15 kilotons. Remember, this is a bomb that leveled an entire city and killed about 100,000 people indiscriminately. And then we're going from that, we're going to 500 kilotons. Okay, and how do we do that? Well, we do that by using fusion. Right, so in addition to the fission component that I told you about, where the uranium fissions, now we introduce tritium into that. And tritium causes fusion, similar to what powers our sun, the heat from our sun, that energy. So we introduce that, and then we can increase the power of the weapon. Okay, so this is a timeline. It shows all the nuclear tests from the beginning, 1945. 1945, there were 3. One was Trinity, which was a test of the first plutonium weapon, and then the 2 that were used in Japan. So there's 3 total. And then in the 50s, a bunch of tests, right? Hundreds. And then you can see which countries performed these tests. You can see the US, USSR, France, Great Britain, China. And these were all above ground tests. So remember, I told you that when the uranium fissions, the fission products are highly radioactive. So in addition to the heat, the destruction from the heat, we have the radioactivity that gets spewed in the atmosphere that causes damage for a long time following the explosion. And we were doing above ground tests then, which means that all of that radioactivity went into the atmosphere. And depending on where the wind blows, you know, that radioactivity would be moved into different directions. So it became clear at the end of the 50s that this was crazy, right? So there was a moratorium, testing moratorium that was proposed, and it was quite successful. So the above ground tests diminished, and we have now the below ground tests that are shown in this graph below this horizontal line. These are all below ground. What that means is we dig a tunnel, maybe under a mountain, and that's where we explode our weapon. Okay, so everything remains more or less contained under the ground. So that's what's shown here. Now, after decades of this test, you know, hundreds of tests, people decided that, well, maybe we should stop these tests. And the Comprehensive Nuclear Test Ban Treaty was opened for signatures. And this treaty is yet to be ratified. There are many nations that are signatories. The US has signed it, but not ratified it yet. And China has signed it, not ratified it yet. But you can see that it's been quite successful. After this, it's been pretty quiet, with the exception of these little black dots here, which are well-known North Korean explosions. So we've had 6 nuclear tests in North Korea. You can see them here starting from 2006 all the way to 2017. Okay, so the NPT is the foundation of the nonproliferation regime. And it was established in 1968. And what it did is it forbids the member states from developing, forbids the states without weapons from developing them. And it also forbids those 5 nuclear weapon states that were at the time, in 1968, there were 5. It forbids them from transferring nuclear weapons capabilities to any other state. So the idea was to curb the expansion of these nuclear capabilities around the world. It also provides assurance through international safeguards, and that's where the IAEA comes in. You can see the building here. That a country could have peaceful programs that don't get diverted into nuclear weapons or other explosive devices. And it facilitates access to peaceful uses of nuclear energy, such as reactors and nuclear medicine and other applications. It also, sometimes people forget to mention this, but it also commits member states to pursue negotiations towards ending the arms race and towards disarmament. But the wording there is pretty vague, right? So it says, okay, well, the 5 nuclear weapon states will disarm. How well that's going? Well, let's see here. So this is the US nuclear weapons stockpile. You can see as a function of time from the 60s all the way to present day. The US had something like 25,000 of these things. So imagine the scale, right? So that's enough for complete global destruction several times over. And of course, the Soviet Union, Russian numbers are very similar, right? So you can see that over the years, several treaties were put into place to disarm, so to reduce that number of weapons. And you can see that the START treaties in the 90s, that caused reduction, and all the way down to the present day. Some of these were very successful. There was a program in Russia with the Russians called the megatons to megawatts program. I don't know if some of you are nodding, you've heard of it. So basically what that did was it took the highly enriched uranium from Russian bombs and it diluted it down into fuel-usable material. So it could be used in reactors. So a very successful program. Okay, so now I'm going to switch gears. I told you a bit about the history, and now we'll tell you a little bit about the research and development that's been going on, including here at Michigan. And one of the things that we're doing is we're leading the Consortium for Verification Technology. And this is a 5-year effort that is funded by the Department of Energy to develop new technologies that can be used for treaty verification. And so here we are addressing gaps and challenges through 6 thrust areas, including things like verifying disarmament. So say that the US and Russia decide to disarm a certain number of weapons. How do we know that that weapon that's being dismantled is indeed a nuclear weapon? And that poses a really interesting measurement challenge for us engineers and scientists, because we want to make sure that what's in that weapon is plutonium, but at the same time, that country that's dismantling the weapon doesn't want to show you all of their secrets, right? So you want to be very sure that it's a plutonium weapon without giving information about the design of the weapon. Very interesting measurement challenge. So over the past almost 5 years, we've graduated a lot of students and published a lot, and we've developed some detectors that are actually being used by the IAEA, by those inspectors. So these are the next generation of detectors that the inspectors can use in the field. So I'll tell you a bit more about that. So this shows a few photographs of students working with detectors, some of our students going on internships. This is a very exciting program. So just about a month ago, we heard that we won a second consortium, which is a consortium for monitoring, technology, and verification that has some new schools within the consortium. So you can see here our team. Obviously, it's a very strong team. It has Michigan at the lead, but also MIT, Columbia, Penn State, Princeton, and so on. So you can see all these schools working together with the national labs to solve some of these very difficult verification problems. So these are some of the expected outcomes from the next 5 years. So developing deeper understanding of the physics, things like fission that I talked about. So fission was discovered in 1939, but there are still many things that we don't know about fission, about how those neutrons fly off of those fragments. How many are there? What is their energy? What is the correlation between the neutrons and the photons that fly off? As well as antineutrino emission from reactors. So reactors emit these subatomic particles called antineutrinos. These can travel for hundreds of miles. And so we can discover a new reactor or monitor a reactor by measuring these antineutrinos. So that's a new topic that we will tackle within the MTV. We're looking for new, better detectors and techniques for monitoring explosions. So we'd like to measure the special nuclear material before we get to a nuclear explosion, of course. We'd like to find it. But in some cases, some countries are able to develop nuclear capability and do nuclear tests, for example, North Korea. And so if that happens, can we monitor what that test was, what was the yield, and where was it, and things like that. So monitoring explosives. So in the rest of the talk, I'll give you a few examples of things that we're working on. Okay, so we do a lot of code development. So we have supercomputers now, and these supercomputers can model what's happening inside the special nuclear material. In this case, this is a highly enriched uranium sphere that you see here. And what you see is that fission chain that I was telling you about and how it propagates within the sphere. So we're able to model that in 3 dimensions. And then we can also model what comes off of this sphere. So we can model the neutrons and the gamma rays coming off of the sphere. And we can also put some detectors out here and try to see, well, how can we detect this piece of highly enriched uranium? Okay, which is obviously very important for a lot of our applications. So in my group, we work a lot on neutron detection. Neutrons are present in our background, but they're emitted by plutonium. And they're emitted by highly enriched uranium when we interrogate it. So if we can detect the neutrons, then we can detect the presence of this special nuclear material. And the way that these detectors work is by interaction of neutrons and photons within the detector material. So what we've done that's new is we've developed some techniques to distinguish the neutrons, shown here in this blob, from the photons, shown in this other blob. So now we have a detector that can detect both types of particles, and that generates a lot of interest for new detectors to detect special nuclear material. In particular, we're looking at these little pillars. They're about this big, so you can make a really small and compact instrument to detect neutrons and photons in the same instrument. So this here shows one of my students working at Idaho National Laboratory with our collaborators, doing experiments on plutonium. So for some reason, they don't let us have a lot of plutonium at the University of Michigan. So we have to travel to these places. Sometimes they're very nice places like Ispra, which is on the lake in Italy, and our national laboratories here in the US. And we measure these materials, and then we look at the neutrons from these materials. And if we analyze the shape of those neutron pulses, we can see curves such as these ones. And we were the first to show that we can distinguish plutonium metal, which is used in the weapons, from fuel. So you can see how these curves are separate from other neutron sources. So if we have a box here and it's emitting neutrons, we can tell you if that box contains plutonium metal. So obviously, who gets the call then is very different, right? If we find, say, at a port of entry or at one of those radiation stations that we have here at the border with Canada, we can distinguish the type of material, the neutron-emitting material that's coming in. Another thing that we're doing in the group is building radiation imagers. So imagers can tell us if a radiation source is present in the room. So radiation is not something that we can see with our eyes or feel. So in order to see it, we need these very sensitive detectors. So this detector is made of the same pillars I showed you before. So now we have a number of these pillars, and we're looking for neutrons that bounce off of these pillars. And neutrons are like billiard balls. They can fly through the air, and they will interact with the pillars. And if they interact twice, we can get a cone. And every cone forms one of these circular traces here. If we have 3 of those bounces, we can determine a hot spot, which tells us where that source is located. Okay, so this is really cool. And if you have more than 3, say 25 of those neutron events, that hot spot becomes even more accurate. So the longer you measure, the more accurate that hot spot becomes. That's 100 events, and so on. Gets a nice image of your neutron source. So if we were inspecting 2 barrels, let's say, we wanted to know where the source is, we could, with this instrument, we could see a nice hot spot in one of the barrels, but not in the neighboring barrel. So this is an example of, here, two of my students at the Nevada test site, measuring a 4.5 kilogram weapons-grade plutonium ball. And you can see it here, and the instrument is in this box here, and we can see a very nice hot spot of that sphere. Here's plutonium with plutonium oxide. So we have 2 objects now in the same field of view, and we see 2 hot spots, which is very encouraging. So the idea is then to take what the instrument tells us and put it on the augmented reality. I don't know if you guys have seen this. I think I see some nods here. So this is the Microsoft HoloLens. So you wear it, and the wearer sees the reality, but then overlaid on reality, you have the image of what you're looking at. And in this case, we had a radiation source placed here, and you can kind of walk around it. So you can imagine, an IEA inspector wearing this and walking into a facility and inspecting where this neutron source is located within the facility. Okay, so hopefully we can detect the S&M before it goes off, but just in case, we need verification for the Comprehensive Nuclear Test Ban Treaty. This treaty seeks to ban all nuclear explosions for any reason. And there's a verification system that's set up around the world. It consists of seismic, radionuclide, infrasound, and hydroacoustic signatures. I'll be telling you about seismic and radionuclide today. This map here shows the location of all these sensors. So if there's ever an explosion that goes off, these sensors are recording, and we can determine where that explosion happened. Okay, so we heard about North Korean tests. This was a recent picture that shows North Korean leader and this object that appears to be a 2-stage nuclear weapon, which suggests a fission component plus a fusion component. And here's a timeline. So 2006 was the first test that was widely regarded to be a fizzle. And what that means is the power of the weapon didn't really fully come out. So that was a very small yield, only about 0.7 kilotons. And it caused an earthquake of a magnitude 4.2. But over time, you can see that the power of these explosions has been getting stronger. So these are more tests. And the latest one, the one in 2017, the yield was between 50 and 250 kilotons. So there's a wide range in the estimates of that yield. That's a lot higher than the previous ones. So the previous ones were of the order of the bombs dropped on Japan, but this last one was a lot stronger, which it was suggested to be a hydrogen bomb, but we don't have any evidence for that at this point. But it might have been a boosted device, given the high yield. So when one of these things goes off, this is a location of the test site in North Korea. We have stations in China and in South Korea and in Japan that give us seismic signatures. And our collaborators within the consortium at Columbia University analyze the shape of these seismic signatures. And by looking at the shape, they can distinguish if what made the Earth move was an explosion or if it was an earthquake. Because obviously we have lots of earthquakes all the time around the world. So by looking at the shape of those squiggles, they can come up with these discriminants. And then the explosions all end up in this quadrant, upper right quadrant. And the earthquakes all end up in the lower left quadrant. So we can discriminate out these two different types of events. Obviously, very important. So the yellow ones are the tests. The green ones are earthquakes. They're actually happened shortly after the latest large explosion of 2017. So that explosion caused a lot of damage to the rock and the mountain in those tunnels. And that mountain, parts of that mountain actually collapsed. And that collapse looks like an earthquake. You can see these green dots there. So it's really fascinating physics here. Okay, but we have a signature for an explosion, but how do we know it's a nuclear explosion, right? It could be a chemical explosion. So the last thing that I want to show you today is looking at the detection of radionuclides from nuclear fission. So these are fission products, and xenon in particular, you may have read in the news, radioxenon. Why do we look at xenon? Does anybody know? It's a noble gas, right? So it can travel a long time. It doesn't really interact much. So near the explosion site, if there's venting into the atmosphere of some of those fission products, what that means is the fission products actually make it into the atmosphere, and they can travel for like hundreds of miles and be detected at a station. And we're talking about a part per billion in the air of these things. So our detectors are extremely sensitive. And we can detect the presence of this radioxenon. This data here is data that my PhD student obtained from the January 16 event. And you can see how sparse the data is. We don't have a lot of data, but we can still pick out the radioxenons, the xenon-133, the 131M. And you can see here that the 131M is kind of overlaid over the xenon-133. So it's hard to discriminate those two isotopes. And we'd like to do that, like to be able to discriminate, to get better sensitivity for these explosions. So we've developed a new detector for radioxenon detection. And we've shown that this, or my student here showed, that this type of detector has better pulse shape discrimination capability, better energy resolution, which gives us better readings on this radioxenon. And reduced memory effect. So memory effect happens when you take a reading and then you take a subsequent one and the detector remembers the previous one. That's a bad thing, so we don't want that. So our new detector has very little memory effect, which makes it very interesting for these types of detections. Okay, so I'm going to conclude now. I hope I convinced you that the discovery of fission was consequential, transformational. It shaped the world that we live in. Non-proliferation play a very important role in stopping the further spread of nuclear weapons around the world. We have safeguards that require international cooperation and legal framework for implementation. We are working on a number of technological developments within our consortium. And here you see a picture of our lab and the NNSA administrator who came to visit us last year. And we're contributing to the detection and characterization of these nuclear materials. So with that, I will conclude. I want to thank you for coming tonight and for your attention. And I'll take any questions.